In May 2022, a NASA engineer sat down at a monitor and opened a file that made no sense. Voyager 1, the most distant machine ever built by human hands, was sending home data that looked like gibberish, long strings of numbers describing an orientation the spacecraft could not possibly be in. If it were really pointed where the data claimed, its signal should never have reached Earth at all. And yet the signal was arriving, strong and steady, exactly as it always had. Something on a machine 24 billion kilometers away was lying to its own creators, and nobody knew why. That mystery is just one piece of what Voyager has detected at the true edge of our solar system, a place where the rules stopped matching the models, where a boundary hotter than the sun let two ancient machines pass through untouched, and where the spacecraft's own instruments recorded something that, to this day, no scientist can fully explain. Almost everything you have ever known has existed inside a bubble, and most people go their entire lives without realizing it is there. The sun does not just sit quietly at the center of the solar system producing light and warmth. It constantly boils off charged particles from its outer atmosphere, streaming them outward in every direction at hundreds of kilometers per second. This outward flow is called the solar wind, and it does not stop at any particular planet. It keeps traveling past Mercury, past Earth, past Mars, past the gas giants, past Pluto and the Kuiper Belt, carrying the sun's magnetic field along with it and inflating an enormous protective envelope around the entire solar system. That envelope is called the heliosphere, and for the first several decades of the space age, it was the only environment any human-made object had ever operated in. But a bubble has an edge, and beyond that edge lies the interstellar medium, a thin, drifting mixture of gas, dust, and charged particles left behind by other stars and ancient supernova explosions. Somewhere far beyond Pluto, the outward pressure of our sun's wind and the inward pressure of interstellar space collide, and where they meet, a genuine physical boundary forms. Scientists call it the heliopause, and for most of the 20th century it existed only as a line in a theoretical model, a rough guess based on physics rather than direct observation. Nobody actually knew where it was, what it looked like, or what crossing it would do to a spacecraft, until two machines built in the 1970s actually got there and found out. Voyager 1 and Voyager 2 launched from Cape Canaveral in 1977, Voyager 2 lifting off first on August 20th, followed 16 days later by Voyager 1 on September 5th, which took a faster, more direct trajectory that let it arrive at Jupiter and Saturn ahead of its twin. Both spacecraft were originally built for a 5-year mission to study Jupiter and Saturn, made possible only by a planetary alignment that occurs roughly once every 176 years. That alignment let engineers use gravity assists from each giant planet to fling both probes farther outward without needing extra fuel. And when Voyager 2's flybys of Jupiter and Saturn went well, NASA extended its route to include Uranus and Neptune as well, giving humanity its first and, to this day, only close-up look at either ice giant. Once both spacecraft finished their planetary tours, NASA did not shut them down. Instead, the agency launched what it called the Voyager interstellar mission, a new and far more ambitious goal: send both probes beyond the outer edge of the sun's own influence and into the space between the stars. Getting there required an enormous amount of engineering foresight that had been built into the spacecraft from the very beginning, because in 1977 nobody could guarantee funding for a mission lasting decades. Each Voyager carries 11 scientific instruments, many with built-in backups, specifically so that a single failure would not end the mission. Each spacecraft has 16 hydrazine thrusters, including 8 backups, a decision that proved critical when Voyager 2's primary thrusters failed after 37 years of continuous use, and its backups, untouched for 4 decades, switched on and worked exactly as designed. Power for both spacecraft comes from 3 radioisotope thermoelectric generators mounted on each probe, devices that convert the natural decay heat of plutonium-238 into electricity. At launch, each individual generator produced about 157 watts, and combined all three gave each spacecraft roughly 470 watts total, enough to run a modern desktop computer. There is no refueling this kind of system and no repair crew that will ever reach a spacecraft this far from home. The plutonium simply decays at a fixed, predictable rate with an 87.7-year half-life. And the silicon-germanium components that convert that heat into electricity also degrade with age, together stripping away about 4 watts of usable power from each spacecraft every single. Voyager 1 reached the boundary first, on August 25, 2012. After 35 years of continuous flight, its plasma wave detector recorded a sudden and dramatic spike, plasma density jumping to roughly 80 times what the spacecraft had measured in the outer Helios heath just before the crossing, accompanied by a sharp increase in galactic cosmic rays arriving from outside the solar system entirely. By every measurement the mission team had, Voyager 1 appeared to have crossed the heliopause and entered true interstellar space, becoming the first human-made object in history to do so. And yet NASA did not announce the crossing immediately. Engineers spent nearly a year quietly checking and rechecking the data before going public, because one specific measurement refused to behave the way every model predicted it should. Existing theory assumed that once a spacecraft left the sun's magnetic influence and entered a region dominated by the magnetic fields of other stars, the direction of the ambient magnetic field should shift noticeably. Voyager 1 detected no such change at all. The magnetic field on the far side of the boundary pointed in essentially the same direction as the field on the near side, a result that made no obvious physical sense and left the mission team genuinely uncertain for months about whether the crossing had actually happened the way the rest of the data suggested. 6 years later, on November 5, 2018, Voyager 2 reached its own crossing point at a different location along the boundary because the two spacecraft had been traveling in different directions since finishing their planetary work. Voyager 1 heading up and out of the plane of the solar system, Voyager 2 heading down and out on the opposite side. Voyager 2's crossing carried extra scientific weight because, unlike its twin, it still had a fully working plasma science instrument on board, giving scientists a direct, rather than indirect, measurement of what was actually happening in the plasma at the boundary itself. Voyager 2 confirmed almost everything Voyager 1 had found. It detected no meaningful change in the ambient magnetic field either, reinforcing that the first result was not a fluke or an instrument error. But it added a second puzzle on top of the first. The sun moves through an 11-year cycle of rising and falling activity, and existing models predicted that the size of the entire heliosphere should expand and contract along with that cycle. Voyager 2 made its crossing during a period of peak solar wind activity, a time when the heliosphere should have been swollen outward to its largest extent. Instead, Voyager 2 crossed the heliopause at almost exactly the same distance from the Sun, about 120 astronomical units, where Voyager 1 had crossed 6 years earlier during a very different phase of the solar cycle. That result directly contradicted what the models expected, and it told scientists that the real shape and behavior of the heliosphere's boundary is far more complicated, more twisted, and more filled with localized fluctuations than any theoretical model built before either crossing had assumed. Before either spacecraft even reached the heliopause itself, they passed through an intermediate region called the Helios sheath, and what they found there turned out to be just as strange as anything discovered at the boundary itself. The sun's magnetic field spins in opposite directions from its north and south poles, and where those opposing spins meet, they create a rippling structure called the heliospheric current sheet, similar in shape to the rings that spread outward when a stone is dropped into still water. As that rippling sheet reaches the termination shock, the point where the solar wind first slows down under pressure from the interstellar medium, it compresses the way ripples bunch up and steepen when they hit the wall of a swimming pool. Both Voyager spacecraft discovered that after this compression, the ripples do not simply flatten out smoothly. Instead, they fold into a churning field of magnetic bubbles, isolated pockets of trapped magnetic field lines scattered throughout the Helios sheath, rather than one clean, continuous boundary layer. This single finding forced a complete revision of how scientists modeled the outer heliosphere, because it meant the region separating our solar system from interstellar space was not a smooth, predictable membrane at all, but a churning, fluctuating, magnetically bubbling environment that no theoretical model had anticipated before Voyager's instruments actually measured it directly. Layered on top of these magnetic surprises is a temperature reading that, on its own, sounds almost impossible to believe. When Voyager 2's plasma instrument measured the environment at the heliopause directly, the plasma came back reading somewhere between 30,000 and 50,000 Kelvin, several times hotter than the roughly 5,800 Kelvin surface of the Sun itself. This is the reading that earned the boundary its informal nickname among some science communicators, the Wall of Fire, a description that captures the drama of the number, but not the physical reality of what actually happens to anything passing through it. The explanation lies in the difference between temperature and heat, two concepts that sound identical in everyday language, but describe very different physical properties. Temperature measures how fast individual particles are moving. Heat measures how much total energy is actually transferred into an object those particles strike. A region can have an extremely high temperature and still transfer almost no heat at all, if there are so few particles present that a passing object is barely ever touched by any of them. Think of the difference between holding your hand briefly inside a hot oven, which causes little harm because air is a poor conductor, and touching the metal rack inside that same oven at the identical temperature, which burns you instantly because metal is dense with atoms ready to transfer energy on contact. The heliopause takes that same principle to its most extreme version. The particles there genuinely are moving at speeds consistent with a 50,000 Kelvin environment, but the region is one of the emptiest measured anywhere in the solar system. So few particles exist in any given volume of space that a spacecraft passing through experiences almost no actual heat transfer at all. That is the only reason two machines built with 1970s technology could fly directly through a boundary hotter than a star and come out completely intact on the other side. For years after both crossings, Voyager 1 continued sending back clean, reliable engineering data about its own systems alongside its science readings. Then, in May 2022, that reliability broke. The spacecraft's attitude articulation and control system, the onboard computer responsible for keeping Voyager 1's antenna precisely pointed at Earth across billions of kilometers of empty space, began transmitting telemetry that made no physical sense. Instead of clear data describing the spacecraft's actual orientation, engineers received long strings of meaningless numbers, information suggesting Voyager 1 believed itself to be pointed in directions that could not possibly be true, because if the antenna had really been aimed that far off target, the signal carrying that very data would never have reached Earth's receivers in the first place. What made the situation even stranger was that everything else on the spacecraft appeared completely normal. Its 4 remaining science instruments continued returning clean, coherent readings about the interstellar medium, magnetic fields, and cosmic rays surrounding it. Its power levels were declining exactly on schedule, nothing unusual there either. Only this one system, responsible for the spacecraft's sense of its own orientation in space, had started speaking in what engineers described as a kind of gibberish, and Voyager 1's own internal safety systems, which are designed to automatically trigger a protective safe mode the moment something appears seriously wrong, never activated at all. As far as the spacecraft itself was concerned, everything was working exactly as it should. Engineers spent roughly 4 months carefully testing theory after theory, constrained the entire time by the simple physical reality of the distance involved, since every single question sent to the spacecraft and every answer sent back required waiting many hours, each way for a radio signal to make the round trip. Eventually, the team traced the fault to an unexpected cause. Something in the intensely radiation-filled environment of interstellar space had caused Voyager 1 to start routing its telemetry through an older, previously retired backup computer, one known to have developed internal faults years earlier, and that older computer's damaged circuitry was corrupting the data before it was ever transmitted home. The fix once identified, was almost anticlimactically simple. Engineers instructed Voyager 1 to switch back to using its correct functioning computer, and the garbled signal stopped. Full normal communication did not actually resume for a couple of additional months afterward, and the underlying vulnerability was not entirely finished, causing problems either, because in November 2023, a separate onboard computer, the Flight Data Subsystem, developed its own comparable fault, leaving Voyager 1 unable to send back usable science and engineering data at all for a stretch of time that was not fully resolved until June 2024. Voyager 1 was not the only spacecraft to have a close call. In July 2023, a routine sequence of commands sent to Voyager 2 caused its antenna to drift just 2 degrees away from precise alignment with Earth. 2 degrees sounds trivial at any normal distance. At more than 19 billion kilometers away, it was enough to break the connection entirely, leaving NASA completely unable to send commands to Voyager 2 or receive any signal back from it at all. There was no simple fix waiting on standby, because the spacecraft could not hear any correction being sent to it in the conventional way. The Deep Space Network's massive dish in Canberra, Australia, resolved the situation using a technique engineers informally called an interstellar shout, an unusually powerful, focused transmission aimed at the general area of sky where Voyager 2 was expected to be, in the hope that even a slightly misaligned antenna might still catch enough of the signal to receive the correction. It worked. Voyager 2 picked up the command, reoriented itself back toward Earth, and resumed normal contact, but not before mission engineers endured a tense 37-hour wait for the signal to travel out, for the spacecraft to respond to the correction, and for confirmation of that response to travel all the way back. A stretch of time during which the possibility that this second spacecraft might simply be lost forever was entirely real. Both of these near misses happened years ago, but the underlying pressure that caused them, a power supply that only ever shrinks, has not gone away, and 2026 has brought that pressure to a genuinely critical point. Voyager 1 now operates just 2 remaining science instruments, the magnetometer and the plasma wave subsystem, after NASA deactivated its low-energy charged particle instrument in April 2026, specifically to prevent a catastrophic undervoltage event that could have damaged other essential systems. Voyager project manager Suzanne Dodd has described the spacecraft's remaining systems as entirely single-string now, meaning there are no more backups left for the most critical components, a stark contrast to the redundant, backup-rich design that carried both spacecraft safely through their first several decades of operation. To squeeze out whatever operational time remains, mission engineers spent 2026 preparing and executing what the team internally calls the Big Bang reconfiguration, a complete remote rewiring of each spacecraft's internal power distribution system, executed entirely through commands sent across billions of miles of space, intended to replace older, more power-hungry electrical pathways with leaner alternatives. The risk is real and severe. If a heater fails to maintain proper temperature during the transition, the hydrazine fuel lines that feed the maneuvering thrusters could freeze solid in the roughly minus 270 degrees Celsius environment outside the heliosphere. And if those thrusters stop working, the antenna could drift out of alignment permanently, exactly the kind of failure that nearly ended Voyager 2's mission back in 2023, except this time with no functioning backup thrusters left to recover. NASA tested the procedure on Voyager 2 first in May 2026, treating it as the trial case for the riskier attempt on Voyager 1 that followed in July. While all of this unfolds, Voyager 1 is closing in on a distance milestone no human-made object has ever reached. NASA has confirmed that on November 18, 2026, at 2:16:07 a.m. Pacific Standard Time, Voyager 1 will be roughly 25.9 billion kilometers from Earth, a distance equal to exactly 1 light day. The span light itself covers in a full 24 hours moving through the vacuum of space. At that distance, a radio message sent from Earth and a reply sent back in response now take a combined 2 full days to complete a single round trip, an ordinary good morning greeting stretched out across nearly the width of an entire interstellar gulf. Here is everything the instruments actually confirmed. laid out plainly. A region exists at the true edge of our solar system where the pressure of our own star collides with the pressure of the entire galaxy. Beyond it, generating plasma temperatures that genuinely exceed the surface of the sun while transferring almost no heat at all. Thanks to how empty that space really is. Both Voyager spacecraft passed through that boundary and detected a magnetic field that refused to change direction the way every model, a helio sheath filled with magnetic bubbles nobody expected to find, and a boundary that sat at almost the exact same distance from the sun on two separate occasions 6 years apart, despite the solar cycle's influence supposedly guaranteeing otherwise. And decades later, with instruments failing one at a time, a spacecraft that briefly forgot how to speak coherently to its own creators, another that nearly lost contact with Earth over a 2-degree drift, and a power supply now split between two machines running on fumes. Both probes are still sending signals home, still adding new data to a body of evidence that keeps forcing scientists to tear up their old models and start again. Voyager did not find a simple answer at the edge of the solar system. It found a boundary that is still, after everything, only partly understood.